So far, we've been looking at circular motion in terms of the tangential velocity and the centripetal force and acceleration, or the acceleration and force towards the center. Now we're going to start looking at it in terms of the radial motion, or what we call the rotational motion. So we have really three types of motion. Those motions are translational, which is where all the particles in the object have the same instantaneous velocity. This is when we talk about, people running and for the most part cars going down a road or throwing a ball, something like that. That's basically our linear motion. Then we have our rotational, which is when we have all the particles in the object have the same instantaneous angular velocity. And so we'll talk about the difference there here in a few minutes. And then we have rolling, which is actually a combination of both translational and rotational. So consider like a tire rolling along the road, or a ball rolling down a hill, something of that nature. So before we can get super into our rotational motion, a little bit about our circle. So we know that the distance from O, our central point, to the circle is what we call the radius, R, and that we can measure within that circle some angle that we call theta. That's what this is here. This 0 with the line through it is the Greek letter theta. So Greek theta. And that's a capital letter. And then this distance that we have from A to B is what we call an arc. And we'll symbolize that with an S as we go through here today. So as we start looking at our angular quantities, we should hopefully recognize the corresponding translational quantities as well. So as we're talking about motion, rather than just regular displacement, which is our translational quantity of change in position, we have angular displacement. And angular displacement is the angle through which an object moves, or a system moves. And we can measure it by looking at the initial angle. So if our baton twirler here starts at 0 degrees, and we always measure 0 at the positive x-axis, and we increase in angle counterclockwise. So our positive y would be 90, our negative x would be 180, and then our negative y would be 270. Okay, so that way we're all working within the same frame of reference. So don't pick a random frame of reference for these problems. Let's stick with this one that I've just given you. So our change in angle is equal to our final minus our initial, just like our change in position in translational is equal to final position minus initial position. But we can also determine the angle through which an object moves by dividing the length of the arc, S, by the radius, R. And both of those will give us the same value. Important to recognize that this angle is going to be in radians, and this angle will only be in radians if these two are as well. And we're actually, all of our work with angular movement and motion is going to be done in radians. So to that end, if you're unfamiliar, what is a radian? A radian is a different way of measuring angles, and it relates the radius of the circle with the arc length. One full revolution around a circle is 2 pi radians. So that's 2 pi. So then halfway, so that's equal to 360 degrees. So then a half a circle, or 180 degrees, is pi. And this unit of radians is going to be our standard unit for measuring angles in this portion of our studies. Okay, we know our degrees: 60 minutes in a degree, 60 minutes in a second, etc., etc. We've been familiar with it, using it hopefully for a long time. So, by definition, a radian is the angle subtended by an arc length s equal to the radius. So, what that means is that when, let's try our green. That we can see. So when this angle s is equal to this length r, that is 1 radian. Okay, and so in any circle, consider as r gets larger, the distance around, or the length of that arc, obviously then has to get larger. And so that value of the radian remains constant. And so within a full circle, with any full circle, we have exactly 2 pi radians. There we go. Which is what we just said, and here we see it. So there's 2 pi radians in one full circle. Our angle is equal to s over r, as we see here, which means that our arc length then is equal to the angle in radians times the radius. But if we quick unit analysis on our radians, arc length is measured in, let's call it meters. And if our arc length is going to be measured in meters, then our radius should be measured in meters. And so what we see is that those units actually cancel out. And so the radian is a dimensionless or a unitless value. So that's, I guess, important, because we see when we write our degrees, we put that nice little circle there. You don't put anything. We can write radians, right? So we can say, radians, okay? But it's actually dimensionless. Our conversions, quick conversion factors: 1 radian is equal to 360 degrees over 2 pi. So 1 radian is roughly 57.3 degrees. Converting between the two is pretty straightforward. Our conversion factor, we can use either 360 over 2 pi or 180 over pi. They're both equivalent ratios. But if I want to convert from radians to degrees, or from degrees to radians, I'm going to multiply by pi over 180 to convert to radians. If I want to convert to degrees, I'm going to multiply the angle in radians by 180 degrees over pi. And that'll give us our conversion. So then we have our actual quantities that we're going to be measuring, calculating, working with. The first is average angular speed. And again, we're going to use that term speed for the most part just to distinguish, because the direction is always going to be changing. Although even really, when we're talking about angular quantities, our directions are really just clockwise or counterclockwise. So in that sense, we're going to be able to go back to using just positive and negative, like we did in one-dimensional motion, to distinguish direction. So our angular speed is symbolized with this lowercase omega. It looks kind of like a curly W, right? Kind of like that. The line over it, of course, just means we're talking about the average. So let's get rid of some of that so it's not so confusing. So the average angular speed is equal to, this right here is our change in angle, right? So again, in radians, change in angle in radians over change in time. So hopefully we see some similarities here between our angular speed equation and our just regular speed equation, or our velocity equation, which was change in position over change in time. Here we have change in angle over change in time. So same thing, slightly different quantities. Right? This gives us our speed in radians per second. When you're working through problems and things like that, you might frequently see RPMs, or revolutions per minute. So just recognize that you'll have to do some conversions to go from revolutions per minute to radians per second. In terms of our signs and notations, counterclockwise is the positive direction, counterclockwise is the positive direction, right? So we go from 0 to 90, we go from the positive x-axis to y, that's the counterclockwise direction. That is positive in terms of angular quantities, and so that means that clockwise is negative. So if we go from 90, from the positive y to the positive x, that's the negative direction in terms of the rotation. Now, we can convert between our angular and our linear speeds, right? So if we have an object moving in a circle, and we consider a point, like we have our record player, and we have some point out at the edge of it. It has some tangential velocity, right? But it also has some angular velocity based on the angle through which it's traveling. And as we saw previously, as this radius increases, the tangential velocity, we'll say Vt here, the tangential velocity is going to get larger, right? V equals 2 pi r over t. So we see there's that proportional relationship. V is proportional to r. The angular velocity, though, doesn't change regardless of the distance from the center, because all of these particles along this point are all connected. And so however much distance some point or some angle out here, whatever the angle this piece out here is, this angle is going to travel through the same amount, or that piece, sorry. So if we have two particles within our record player at two different distances from the center, or two different radii, the actual linear distance through which they're going to travel is going to be different, but the angle through which they travel is going to be the same. So the one further out is going to have a larger tangential velocity than the one closer in, but they will both have the same radial velocity. But we can convert between the two. And as I said, the tangential velocity is proportional to the radius. And so if we want to determine the tangential velocity at some radius at a given angular velocity, we simply multiply the angular velocity by the radius. And so again, we can see that at a constant angular velocity, as the radius increases, the tangential velocity will increase as well, right? And just unit-wise, we have our radians per second, and remember that radians isn't really a unit. And then we have meters, and so we end up with meters per second, because that's not really a thing. It's really just 1 over seconds, cycles per second, if you will. Then we have our angular acceleration, and similar to how our translational acceleration is change in velocity over change in time, our angular acceleration is change in angular velocity over time. And our symbol for angular acceleration is a lowercase Greek alpha. So it's still keeping with the A for acceleration, except now we're using the Greek letter instead of the English letter, regular letter, our letter. And then from a unit perspective, and because our change in rotational velocity is radians per second, and then time is seconds, our units for angular acceleration are radians per second squared. We're going to maintain our counterclockwise is our positive direction, and clockwise is our negative direction. But again, as we consider linear or translational acceleration, a positive angular acceleration is an acceleration that is occurring in the counterclockwise direction. If the motion, if the circular motion is already going in that direction, and the acceleration is that direction, then it's going to speed up. If you have an object that is rotating clockwise, so it's moving in the negative direction, and the acceleration is counterclockwise in the positive direction, then the object is going to be slowing down. Now, similar to how we are able to fairly easily convert between angular and tangential velocities, we can also easily convert between angular and centripetal accelerations. And so let's change that back to blue. Our centripetal acceleration is going to be equal to the angular acceleration times the radius. So again, we see that proportional relationship between our angular quantities and our translational or centripetal quantities as they're tied together by the radius. We get further out, and that centripetal acceleration is going to be larger. Again, though, keep in mind that the directions of these accelerations are different. The centripetal acceleration is always going to be towards the center of the circle, as we've been talking about. The angular acceleration is going to be either clockwise or counterclockwise. Now, one other equation, one other derivation, just to show you really quickly, we also know that centripetal acceleration is equal to v squared over r, which we talked about last week or the week before. But we should recognize then from the previous slide that the velocity is equal to omega times r, where our omega is the angular velocity, and r is, of course, our radius. So a quick derivation, we can plug that in for our velocity, and we get another way of looking at the centripetal acceleration. Centripetal acceleration is going to be equal to omega squared r squared over r. So we're going to cancel out one of our r's. So centripetal acceleration is equal to omega squared r. So we can then see how our centripetal acceleration ties to our angular velocity and the radius. Notice that we're still proportional to the radius and then proportional to the square of the angular velocity. So what that means is if we double the angular speed, we're actually going to increase the centripetal acceleration by a factor of 4. Now, just a few quick notes to compare our variables and then our equations. And again, to re-emphasize the correlation between our angular and our linear motion. We have the same sets of variables for both, just slightly different in terms of what they describe. So for linear, we have our position, which is measured in meters, and it's symbolized with an x. For angular motion, we talk about that change in terms of the angle in radians. So then we, of course, have the displacement, which is the change in position, the angular displacement, which is the change in angle. In the linear set of calculations, we have our velocity, which is meters per second, so change in position over change in time. On the angular side, we have angular velocity, which is change in angle over change in time. And then we have our linear acceleration and angular acceleration, which are the rates of change in the regular velocity or the linear velocity, rate of change in the angular velocity, and then, of course, our time, which is consistent throughout. So then we can take a look at our linear and angular equations and hopefully again see the similarities between the two. So we've put our angular motion equations in the same format as our as what we're comfortable with for our linear motion. So our first one here is our final position, or our final velocity rather. So Vx is equal to our initial velocity in the x plus the acceleration times the time. So this part here represents the change in velocity. Here's our initial velocity. We have the same equation for angular motion. Our final angular velocity is equal to the initial plus the angular acceleration times time. So this represents the change in the angular velocity. We have final position, which is equal to initial position plus vt plus 1/2 at squared. So this is our relationship between position and time when the velocity is uniformly accelerated, right? This is our quadratic. We actually have basically the exact same equation for accelerated motion. This gives us our final angular position. So on that 0 to 360, it's going to tell us where we're at any given point, assuming the acceleration of the system is constant based on the initial position and the time. We have our Vf squared equals Vi squared plus 2a delta x. This is the equation that relates final and initial velocities with the acceleration and how far or what the distance is through which that object passes as it accelerates. We have the exact same equation over here, where our final angular velocity is equal to the initial angular velocity plus 2 times the angular acceleration times the change in angle. And guys, something to keep in mind as we talk about these changes in angles. A circle is obviously 360 degrees or 2 pi radians, but as an object is accelerating, it might go through multiple rotations. It might go through 8 pi, it might go through 10 pi. And so we don't have to focus on just a single revolution, because a lot of times we have rotating objects that are moving for multiple rotations, maybe hundreds of rotations. You have something like a centrifuge that's moving very, very fast or spinning very, very fast. As it accelerates up, it might go through 100, 200, 300 revolutions before it's up to speed. And so this change in angle is not limited to 2 pi. It can be, if it's going through multiple cycles, then put that full angular displacement in there. Okay, so it doesn't necessarily have to be 2 pi or less. It can be any value, depending on how many rotations it goes through. Then our last equation is basically our average velocity, time, and change in position equation. And so our linear kinematics version of this tells us that the change in position is equal to 1/2 Vf plus Vi. This part here simply tells us our average velocity. And so our average velocity times a change in time is going to give us our change in position. The angular version of this tells us that our total angular displacement, delta theta, is equal to 1/2 omega f plus omega I times delta t. This 1/2 omega f plus omega I is than really just our average rotational velocity. So our average rotational velocity times the change in time gives us our total angular change in position. So I think the big thing to recognize here as you're working through angular scenarios is to understand that while our specific situation is a little bit different, the approach, the equations are really the same. And so again, we're applying the same ideas, the same motion ideas to a rotational system, but we're doing so in a very similar way. And so just because we're rotating doesn't mean that we need to completely change our approach, completely change our ideas about how these work. Okay? Great.